should be pretty apparent if you think about it for a moment that different vectors can span the same set. Let's consider a simple example. Let's look at the span of the vector 1, 2 in two-dimensional space, and let's compare it to the span of the vector -2, -4. Okay? So the span is the set of all linear combinations of the set of vectors. When we have just one vector, it's going to be the set of all scalar multiples of that vector. So vector 1, 2 right here, say, and the span is going to be all linear combinations of that vector, all scalar multiples of that vector. And so if we multiply it by a positive scalar multiple, we could go in this direction. So any vector in this direction is in our span. But also, if we multiply it by a negative scalar multiple, we would go in this direction. So any vector in this direction is in our span. So we get a line in two-dimensional space, right? Now let's consider the span of vector -2, 4. So again, let's start by plotting vector -2, 4. -2, -4. So -2 and then 1, 2, 3, 4 down. Notice it's pointing along the same line, and if I take scalar multiples of this vector, I will just lie on the same line, okay? Which means every vector that is in this span is also in this span, and vice versa. Their span is the same set of vectors. They are equal. They span the same space, okay? So we want to be able to know when two different spans, if they're really equal. All right, so to do that, we first need to learn some terminology regarding general sets. So let's consider two sets. And let's call them S and T. Okay, remember a set is just a collection of stuff. It could be a collection of numbers, it could be a collection of vectors, or just about anything else. So just, you know, a collection of some stuff, another collection of some stuff. Okay, the question is, are they the same set of stuff? So if for every element, let's say A in set S, we have the element A is also in set T, then we say that S is a subset. Let me write it out first. We say S is a subset of set T, and write S and then the subset symbol is this one, okay? Technically, this is a subset or equal to symbol, okay? The idea here is that, hey, we have S here, okay? And everything in S is also in T. So maybe this is T. So every point in S, well, it's also in T, right? But not necessarily vice versa. the elements in T don't have to be in S. Okay, in that case, we say S is a subset of T. Okay, if S is a subset of T and T is a subset of S, then the two sets are equal. Okay, in other words, if every element of S is also in T, and if every element of T is also in S, that means they must have all their elements in common. And we say they are equal. Everything in S is in T, and everything in T is in S. They have exactly the same members to both sets. Okay? Now, a span is a set. It is a set of vectors. So if we have a span of vectors, say v1, v2, all the way to, say, vk, and a span of vectors, and actually, let me give these names. Let's let v equal the span of vectors v. v1, v2, all the way to vk. Okay, and let's let w be the span of vectors w. So w1, w2, all the way to vj. Okay, now v and w are sets. These are spanning sets. It is the set of, so vector v, or set v here, is the set of all possible linear combinations of this spanning set of vectors. Set w is the set of all possible linear combinations of the spanning set of vectors w1, w2, all the way to wj. Okay? Then, because they're sets, they will be equal if v is a subset of w, and also w is a subset of v. If everything inside v is inside w, and every vector in w is in v. Okay? But because these are spanning sets, every vector in v can be expressed as a linear combination of these vectors, can be expressed in terms of these vectors, which means we don't have to check that everything in v is in w. We just need to check this spanning set of vectors. Okay? Every one of these vectors in the spanning set is in w, then vector v, or set v, will be a subset of set w. Similarly, we don't have to check every possible linear combination of these vectors, because every linear combination of these vectors can be expressed in terms of w1, w2 to wj as a linear combination of these vectors. So as long as these vectors are in v, then set w will be a subset of set v. Okay? So let me write that out a little more formally to convince you. Let's say this is a theorem. In fact, yeah, let's say this is a theorem. So let me just rewrite some of what we're dealing with here. So set v is the span of vectors v1, v2 to vk. And w is the span of vectors w1, w2 to wk, or wj rather. if v1 and v2 and all the vectors in the spanning set for set V, if they are in set W, then set V is a subset of set W. Okay? Let's prove it. So remember the definition. In order for a subset, for a set to be a subset of another set, that means every element in this set must also be in this set. Okay? So I'm going to start by taking an arbitrary element in set V. So let vector V be in set V. Okay? Now, V isn't just any old set. It is a spanning set of vectors, which means anything in V can be expressed as a linear combination of these vectors. So by definition, then our vector V is equal to A1 V1 plus A2 V2 all the way to AK VK for some scalar constant scalars A1, A2, all the way to AK. Okay? Now, I need to show that vector V here is also in set W, which means I need to show it is in the span of these vectors, which means I need to show that it can be expressed as a linear combination of the vectors W. Okay? Now, to do that, we're going to use this fact here, that vectors v1, v2 to vk, they are in W. We are assuming that fact, if this is true, right? So since we're assuming that fact, let's use it. Since v1 and v2 all the way to vk are in set W, we have, if you're in a spanning set, you can write each vector here as a linear combinations of the spanning set of vectors. So I could write each of these v's, each one of these, as a linear combination of the vectors here, since each one of these v's is in set W. Okay, so I'm using the definition here at each step. So V1 must be equal to some set of constant scalars V1j Wj. So V1 must be equal to some set of constant scalars, and I've double indexed them because I'm going to have to do it again for V2. So some set of constant scalars times the spanning set of vectors, comma, and V2 must also be a linear combination of the vectors W. So B21 W1 plus B22 W2, and so on. Okay, notice you could think of the subscripts here as telling me the row and column. So this is for, or you could think of them as applying to, you know, the first number here applies to the subscript of V, the second number applies to the subscript of W. Okay? And we keep doing that until we get to the very last V. W1 plus BK2 W2 plus dot 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 plus BKJWJ. Substituting into our first equation. Oh, actually, I need to state what the B's are. I don't state that in your proof. You got to be very clear in your proof what all the elements are that you're using. Where B, B11, B12, all the way to B, 1J to B21, and I'll just go all the way to BKJ. These are all constant scalars. So all those B's are just constant scalars. Okay, now let's substitute into our first equation. So substituting these into our first equation, we have, so let me just be clear what I'm doing here. I've expressed V1 as a linear combination of the vectors W. So I'm going to take that and I'm going to substitute it into V1 in our first equation. I've expressed V2 as a linear combination of vectors W. So I'm going to substitute that into the V2 in our first equation here. And I'm going to continue doing that for all of the V's. Okay. So our original vector V is equal to A1 times V1, but I'm going to swap out V1 for this expression here. Okay, so it's equal to A1 times B11 W1 plus, I'm going to go all the way to B1JWJ. And then let's go to the next term, so A2V2, but I'm going to substitute out V2 for this expression here, this linear combination of W's. So that's A2 times V2 expressed as a linear combination of vectors W. And I keep doing that until I get to the very last vector, which is vector VK. I'm going to swap that out with this linear combination. So that's BK1W1 plus all the way to BKJWJ. I have just about enough room. Okay. All right. And now all I'm going to do is rearrange, combine like terms. Okay, so if I combine like terms, I notice I have A1B11W1, and I have A2B21W1, and I have AKBK1W1. So I'm going to combine all those W1 terms together. So I have A1B11 and A2B21 all the way to AKBK1W1. Okay, and I haven't written it down, but we could do the same thing for W2. W2 would be A1, and W2's hiding in here somewhere, but it'd be B21. No, I'm sorry, B12. So A1, B12, if I distribute it to the coefficient of W2 hiding in here, that'd be A2 times B22. Keep on doing that until you get to the coefficient of W2 hiding in here. That'd be AK times BK2. And this should not have an arrow over it. That's not a vector. And we keep going until we get to the last W. Okay, so if we look at the last W, Wj, that's A1 times B1j Wj. And that is a vector. So A1 B1j plus A2 times B2j plus, and you keep on going until you get the last term over here. So that's AKBKJ. Okay, all right. I know this is complicated, but note that in each case here, I have a scalar times a scalar plus a scalar times a scalar plus a scalar times a scalar, right? So once I multiply and add up all those scalars, this is just going to be a scalar number, whatever this nasty expression is. Okay? This right here, same thing. This will just be a scalar value. So what's in front of each Wj here is just a scalar value. So I have a scalar times W1 plus a scalar times W2 plus a scalar times the last W, okay, and all the W's in between hiding in here, which means this is a linear combination of the vectors of W, right? Scalar times a vector plus a scalar times a vector plus a scalar times a vector. That's a linear combination, which means we've expressed vector V as a linear combination of the vectors of W. And since vector V is can be expressed as a linear combination of the vectors W1, W2, all the way to Wj, it follows that vector V is in set W, which is just the span of the vectors W. Okay? That's what it means to be in the span, right? You could express this as a linear combination of these vectors. We've just showed we can express V as a linear combination of these vectors, so V must be in this span. Okay? Now, the only thing we assumed about V, vector V, is that it was in set V. It was in this span. That was the only thing we assumed, which means this must be true for every vector in this span. Because it's true for every vector, it must mean that by the definition of subsets, right? What did we say here? If every element in one set is in another set, then we have the first set is a subset of the second set. And we just showed that. Therefore, since every vector V that is in set V is also in set W, it follows that V is a subset of W. And we have proved what we want to prove. Okay? This one's a little more complicated than what we've done in the past. Okay, it's okay if you didn't quite get all of it, but try to understand the main thrust of it, the main argument. Okay, there really isn't anything too complex that we're doing here. It's more death by symbols. We're dealing with a lot of symbols, and we just have to manipulate them. But the big idea is, okay, let me sum up. We have two spanning sets. We are assuming that the spanning set of vectors is in set W here. Okay, which means that every one of those vectors can be expressed as a linear combination of the vectors in W. Now, if we take any vector in set V, we can express it as a linear combination of vectors v1, v2 to vk. But each one of these is a linear combination of the vectors in W, w1, w2 to wj, right? So if each one of these is a linear combination of the vectors in W with some algebraic manipulation, which we do here, kind of looks complicated, we could show that V is also a linear combination of the vectors in W, which means this vector V is in the span of those vectors in W. That's going to be true for every vector V in set V. Okay? Because the properties we use hold for every vector in set V. Which means set V is a subset of set W. Okay? So we're going to use this property in the next example. Okay? In order to show one set is a subset of another set, we just need to show that every one of its spanning vectors is in the other set, can be expressed as a linear combination of those other vectors. Okay? And if we want to show two sets are equal, we need to show every one of those vectors in the spanning set are in the other set. And vice versa. We need to show every one of the vectors in the second spanning set is in the first set. And if we could do that, we will have shown that the sets are equal.